Hello, my name is Kristiane and today I'll be presenting my results for Lab 2, Motion of a Falling Object. So, what's the objective for this lab? In this lab, we want to analyze the motion of an object. In my case, I used a paper ball during free fall, using Newton's second law, the momentum principle, which is this one you can see here. In this occasion, the net force acting on the falling object is not zero because there are two forces adding up to the net force acting on the paper ball. One of them being the weight force, which is equal to the mass of the paper ball times the gravitational constant, and the second force being turbulent drag force, which is equal to the proportionality constant of the drag force times the velocity squared. So how will we do this? I did this by tracking and graphing the motion of the paper ball using Tracker, and then comparing it to two different computer models. One that accounted for drag force and weight force, and one that only accounted for weight force. These are the results as you can see here. So first of all, let's analyze our observed model. So when tracking the motion of the paper ball in Tracker, we can see that the graph modeling the position of the paper ball with respect to time is a downward, non-constant slope line graph. This non-constant slope shows how the object was accelerating due to gravity being exerted by the ball on our system, which is the paper ball. This goes to show how, in this occasion, F net is not equal to 0, since our velocity final is not equal to our velocity initial. I made a choice on the axis, putting the origin on the center of the paper ball before it was moving, and the object moving in the negative y direction. Before moving on to showing the computational models, these are the two free body diagrams that represent the computational models. Model 1 is only accounting for the weight force, which is going in the negative y direction, and Model 2 is accounting for both weight force and drag force. Now let's take a closer look at the predicted model code that didn't account for drag force and only accounted for weight force. Our initial position and our initial velocity vectors are both 0, since we start from rest. We chose delta t to be a very small time step, and of course, the gravitational constant is 9.8 meters per second squared. The unit vector shows the positive y-axis. To predict the motion of the paper ball, we will analyze the motion of the ball at t is less than 0.667 seconds, which was the time at which the ball stopped moving and which we got from our tracker. Now, since this model only accounts for weight force, our net force is only the weight force, which is the ball's mass times the gravitational constant times our unit vector. Now we apply the momentum principle and derive our updated velocity and our updated position formulas. One being that our final velocity is equal to our initial velocity plus the net force acting on the ball divided by the mass of the ball times delta t, and our updated position being final position is equal to initial position plus the velocity of the ball times delta t. Now let's take a look at the predicted model code that did account for drag force. Now, instead of only having to specify the gravitational constant, we also have to specify the proportionality constant for the magnitude of drag force, which was estimated through trial and error. This constant gave the most accurate end position when compared to the end position that we observed on Tracker. So now the net force will account for both the weight force and the drag force. The drag force is now the proportionality constant, which is 0.0009, times the magnitude of the velocity of the ball, squared times our unit vector. Now again, we apply the momentum principle to derive our update velocity and our update position, and this concludes this computational model. Now let's take a look at our results and compare them. As you can see, the observed position, which is the blue line, is almost identical to the predicted position model that did account for drag. However, the predicted computational model that did not account for drag and only accounted for weight force is overestimated. The position of the paper ball is overestimated. Why is that? Well, if it doesn't account for drag force, that means that our paper ball would be moving faster. However, in real life, of course, drag force has to be accounted for. So now let's think. Which models, if any, predict the terminal velocity? This would be the drag force. This would be the computational model that accounts for both drag force and weight force. Since our drag force is what gives us an actual terminal velocity, and only accounting for the weight force is not enough. Now let's imagine if the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? The answer is yes, though our initial velocity would not equal 0, which compared to our observed model, it was 0 since our ball was at first at rest. The object will still have the same terminal velocity because that's just how drag relates to velocity. It opposes it, so the more velocity there is, the more drag. Here we can see a computational model that has an initial velocity of -2 meters per second. we can see that the terminal velocity is the same as that of our previous computational models. So in conclusion, the model accounting for drag force and weight force was the most accurate representation of the paper ball's motion. 2. Regardless of the ball's initial velocity, it would always level off to a terminal velocity like previously discussed.